Hello, and welcome to the second part of this video series. In this video, we'll be utilizing the expressions that we got in the previous video, along with explicit differentiating through our Python code to illustrate and simulate what is going on with this bar profile. Well, what is this bar? Where do we get this bar from, and what temperature profile do we want to illustrate? Well, we are given a bar, one-dimensional bar of length 20 meters that is initially at room temperature of 20 degrees Celsius. Is initially at time equals 0, is heated at the left side at 50 degrees Celsius. The right hand side is heated at 80 degrees Celsius. So we want to demonstrate how this looks on a graph, right? So first of all, we want to be, now that we understand what we're dealing with, we want to go ahead and utilize our expression from our last video. It won't be the last one, but if you recall, we determined for the x direction as well as the x, y, and z. In this situation, it is bar profile and it is only one direction, so we're only going to use the x direction, the first equation that we got. And it's not going to be with alpha a little bit behind, so we can go ahead and tweak it out a little bit. So the expression that we'll be starting with is that the constant k multiplied by the second derivative of temperature with respect to x squared plus the heating generation rate is equal to rho Cp times the temperature with respect to time. All right. This is kind of what we ended up with the last video, and however, in this situation, we're having this bar profile and there is no heat generated in this, so this Q is equal to 0. We get rid of that, and when we do that, we get this left-hand side is equal to this, so we're going to go ahead and divide the thermal conductivity coefficient by rho Cp, so that we can go ahead and get the thermal diffusivity coefficient, alpha, right? So we get K divided by rho times the specific heating capacity times the second derivative of temperature with respect to x squared is equal to partial derivative of temperature with respect to time. Beautiful. And then, of course, this K over rho Cp becomes alpha, so that we get alpha times second derivative, partial derivative of temperature with respect to x squared is equal to partial derivative of temperature with respect to time. Beautiful. Now what we want to do here is get the explicit differentiation of these two expressions, right? The second partial derivative of temperature with respect to x squared and temperature with respect to time. And what we're going to be doing for the first one, I'm going to start off with the first expression, but as you can recall here, we said we have 20 meters long and we have delta x is 1 meter. What we're going to do is break this bar up into equal increments of 1 meter so that we get 20 equal increments throughout this bar. Now, this drawing might not be perfect, but just imagine that there are 20 equally sliced pieces in this bar, starting from j equals 0 all the way to, of course, j equals 20. All right, we have 20 meters. They're each 1 meter long. We have 20 of them. All right. So we're going to be using that for our expression of temperature with respect to position. And we're going to start off with the first derivative instead of the second. So partial derivative of temperature with respect to x. What we have to do is compare one of these temperatures with the box prior, right? And how we do that? Simply by equaling j plus 1 minus t of j. And divide it by the difference, right? How much it changed, what it changed by, which is increments, delta x. Right? So this is our expression for our first partial derivative. The difference between the two temperatures divided by the increment. Now, if you want to find the second partial derivative of temperature with respect to x squared, now what we want to do is the derivative of this, right? So this, we're getting the slope of this bar, or of this box, right? And what we want to do is get the increment 4 and compare the two, right? So what we need to do is subtract this from the Q prior, right? So we get this remains out front of plus 1 minus t of j and delta x. And then subtract, like I said, the slope of the prior. So prior we do j, and then we have j minus 1, right? And then, of course, over delta x. Of course, this whole thing is all over delta x, right? We can go ahead and simplify this into a common denominator so that we can simplify this a little bit so that we end up with t of tj plus 1, and then we get minus t of j minus, so we get 2 minus 2 t at j, and then minus minus we get a positive t j minus 1. Of course, this is all over delta x squared. And there we have it. There is our expression for our second partial derivative of temperature with respect to position. Now, what we want to do is find the first partial derivative of temperature with respect to time. And this is a little bit easier to think, but not to get there. So, like this, we're going to have equal increments of time throughout. And so what I'm going to do is make t equals to n times delta t, right? As later on in our Python code, we'll be able to kind of mess around with our delta t values, so we'll get a total time. And of course, we're going to have a total number of equal amount of time throughout this. And I thought about that. All of these expressions down here are all happening at the same time. Time is not a factor here. So this is all when n at time n, right? I don't need to do all of these, but just to clarify the picture a little bit, we want these to be all at the same time. Meanwhile, for a partial change in temperature with respect to time does not. So what we want to do here is, of course, change of temperature. We're going to do the same thing, but we want to change between the time. And what we want to do is we're going to keep the same increment, same value of j. However, you're going to switch around the time, right? So that what we get is t of j at time n plus 1 minus t of j at time n. It's all over the change the partial increments, which is delta t. All right. So we have it for first. That's all we need. Now we can simplify this by equaling them to each other, putting them back into this expression, right? So then we get alpha times, and we set the second derivative down here. I'm actually going to pull out this delta x squared to simplify this a little bit, and then just multiply it by the top, which is t of j plus 1 times n minus 2 t j at time n minus t j minus 1 minus 1 at time n. That's a plus. I don't want to mess that up. J then j minus 1 n. All right, and then I'm going to equal it to the right hand side, which is partial derivative of time or temperature with respect to time. Right. Stop. Again, what I'm going to do is multiply this delta t out, so it comes out here, and then we're going to have leftover tj at n plus 1 minus tj at n. Beautiful. There we have it. This is a good expression, but we can go ahead and simplify this even more. As I said, this value should be somewhat constant, as we are going to have the value for alpha, value for delta x, we're given to put to 1 meter, and then delta t is also something we're going to be changing. So I'm going to rewrite this the value of r and multiply it out so that we get an answer just for this value, right? So if you multiply this out, and we have to add this back onto this other side, you see that j at time n is equal to this, right? So we're going to have negative 2r, and we're going to have plus 1, right? So I'm going to go ahead and multiply this out. First term, we're going to have r times t j plus 1 time interval n. Like I said, we have 1 minus 2r. So plus 1 minus 2r of t j at time n, right? Then plus 1 more r. R at t of j minus 1, of course, at time n. And then this is going to be equal to our temperature at j at the time after, j of n plus 1. There we have it. There is our final expression. And now all we have to do is go ahead and plot this into our Python, put in our nodes, and plot it out, see what it looks like. So let's go ahead and do that. Hello, and welcome back to Collaboratory. Now that we've gone ahead and solved for that equation, let's go ahead and plug that into Python code to go ahead and solve for the temperature profile of this bar. While solving for this temperature profile, let's make some plots as well to see what it looks like over time. So as always, I've gone ahead and imported numpy as np, as we're going to be needing it throughout this code. And then, of course, make some plots, as we want to say, like I just said, we want to make some plots of this temperature profile over time. As always, I like to start off with our givens, with our knowns. So if we go back to where we're given, we recall that the length, this bar has a length of 20 meters. It has a thermodiffusivity of 1 meter squared per second, and the spatial increments of 1 meter. And also, we want to start off by limiting the maximum time step to 0.5 seconds. So with that being said, let's go ahead and plug in our nodes. We know that alpha is equal to 1. We know that we said dt, we want to start off with 0.5. We'll see later on why. Dx, we want to keep it at 1. And then what else do we know? The temperature. We know that starting T0, starting at 20 degrees Celsius. We know that the left-hand side, we call it T left, is being heated at 50 degrees Celsius. Right? You know, the right-hand side, we call it T right, is being heated at 8 degrees Celsius. Right? That's pretty much. We also solved for R. It was a little mixture of these knowns, so I'm going to go ahead and plug that in to save us some time. If we recall, R is equal to alpha times dt, simply divided by dx squared. Right? Those are all of our knowns, along with the bar being 20 meters long. Right? However, we already said that we have spatial incrementations of 1 meter. So I'm just going to go ahead and call n, which is going to be our increment, our amount of increments. We're going to have 20 different increments of 1 meter long. 20 times 1, we have a 20 meter long bar. Right? Cool. Then we also want to start creating a list for temperature, right? We want to have 20 different increments. So what I'm going to do is call npfull, function that makes us have a shape of n, like we just said, 20 different increments. And we want it to be filled with the starting temperatures, the initial temperatures, which is T0. Right? So that looks good. If we press T, shift enter, we should get 20 different increments, all at 20 degrees Celsius. If you see, that's what we get, an array of 20 different values, all at 20 degrees. Beautiful. However, it's not all at 20 degrees. Like we said, the left and right hand side are at its values. So what I'm going to do is splice this. So we want this first value to be 50. So this is T0. Okay. 0. Starts at 0, and we said we want to make this T left. And then the right hand side, this very last variable we want it is -1. Grab that and call it T right. So if we go ahead and run this again, this first one should be 50 and this last one should be 80, right? And that's what we see. Beautiful. So now what we want to go ahead and do is run a for loop with our given equation so that we see how the temperature reacts over time, right? So I'm going to go ahead and add a new code, hold up our picture from our derivation in the first half of this video. So I'm going to put in this final equation we have here. So I'll start off with the right hand side, t of j n plus 1. We're just going to simply say that it's going from 1 to negative 1, right? That's what we want to gather, right? All of these values in between, right? Going from here to 20, right? These 18 values in between. So start off with this first value, r times t of j plus 1 times n. So what does this mean? We're adding 1, so 1 plus 1, that equals 2, and then 1 minus 1, that equals 0. So it should be 2 to 0. So I'm just going to put 2 semicolon, just to keep it simple. We're adding this 1 minus 2r, so 1 minus 2 times r. Then we're multiplying that by tj of n. So this is where things might get a little confusing, but we are going to be using from 1 to negative 1. What this means is we're simply getting the temperature of that increment at that specific time will depend, or the temperature that we're getting is dependent on the temperature that we have at that special increment. So this is necessary to have, and sorry if that made it a little confusing, that was a good explanation, but we have plus r, then we have to multiply the second one, this final one, which is j minus 1, so we're subtracting 1 from all these values, so 1 minus 1 again is 0, and then negative 1 minus 1 is negative 2, so we're just going to go from 0 to 2. If I press shift enter, and run t, now these should somewhat look like they're mixing in, and it does. So from 50 to 20, it goes from 50 to 35 to 20, and from 80 to 20, it goes from 80 to 50 to 20. So that looks all good. Now, sorry, like I said, we want to create a for loop. We want to continuously run this out. Right? So what I'm going to do, for I in range, start off, we'll just say with 100 different values. Right? Then we want this in there. Right? And then let's just, for fun, let's print t, see what it looks like. If you can see, this is all the values for 100 different times, starting off like we said, 30, 50, 37, 25, and it's slowly but surely transcending over time as each incrementation is heating up. If you go to the bottom, we see it reaches substantial temperatures. So we know that's looking good. What we want to do now is not print it. We want to graph it, right? Make some subplots. So I'm going to go ahead back here and make subplots, right? So fig 1 was make subplots, right? And actually, before I make this, what I want to do is make, for the x values, as we're going to have to make the subplots, we're going to have 19 different increments instead of 20, right? Because values for 0. So what I'm going to do is call it x, because that's going to be our x value. Call it MPA range, put in n, so that gives us 19 different values. So then now we can go ahead and fig1 dot add scatter. We go ahead and plug in our values. So for x, we're going to have an x, or our x values, and for y, we're going to have our temperature, right? And then mode, let's just make it lines. Keep it nice and simple. All right. Okay, so this is what our temperature profile looks like originally, right? At time equals 0 when the left hand side is at 50 degrees, the right hand side is at 80, and everything else is at 20 degrees Celsius, right? So now what we want to do is make it back into here so that we can update this plot and add all of these values in there, right? So what I'm going to do is copy and paste this last one. We add scatter, and then one.update layout. What do you want to do? You want to make the height. Let's make it 100, and let's make the width 800. Right? And let's see what that looks like. Ooh, I think I made this a little too low. Okay, there we go. That's why. Let's make this a little bit bigger, actually. Okay. Make this 1,000. Okay, looks a lot better now, right? But if you can see, we have way too many different values, and there's just called traces. So there's two things I want to do is kind of clean this up a little bit, get this letter less, as well as name these better. So you can go ahead here, simple name. I don't think we need this in here. Just go straight to this one. What do we want to call this? So we want to name it string. Alright, we want to see what it looks like. It might just be one. Alright, see what that looks like. Alright, so there we go, looking pretty good, right? However, this is a lot of different lines. We want to kind of shorten this, so what I'm going to do is create an if statement in here. And I'm going to say if percentage of I is possibly divided by 10, not 0, and this will simply gather every other 10 values pretty much. So let's see what that looks like. Looks a little bit better, but it's still pretty messy. What we can do, let's clean this up a little bit. However, we don't reach the full effect that we were looking for, so I'm actually gonna make this a little bit bigger. What I'm gonna do is make this range, see what that does. If we do 1 to 500, you can see we get all of these beautiful lines. That is exactly what we're looking for. So now if I make this even smaller, if I do 525, even less, looking a little bit better around this back. A lot less lines, and it's looking pretty clean. These last few ones are almost perfect for ideally what we're looking for. So that's it for today. Hopefully you guys found this video useful, and I'll see you guys in the next one. Thank you.